So concept zero with alternating current is the notion that that the current that goes through our transmission lines, that's in our power grid, that's generated by Bonneville, et cetera, that we pay Portland General Electric for, is alternating current. And why this is, we'll learn in the next chapter, but the short answer is that alternating current can be easily and passively stepped up to really, really high voltages for reasons that we'll learn this chapter. Okay, we can step it up to really, really high voltages, transmit it over long distances, step it down, transmit it, into a hierarchical sort of system where we step it down, and locally, it's probably transmitted underground to those little boxes in your backyard about 10,000 volts, and then from there it's stepped down to like 110 volts, which is relatively safe as long as you anyway. And in the United States of America, the frequency by which it goes positive, negative is 60 hertz, and that's the entire power grid west of the Rockies is one contiguous unit or whatever, and it is all in unison. It is all operating in unison, and exactly how that works, we'll maybe talk about that when we get to generators and stuff like that. But yeah, there it is, right? So now I'm going to hit the little thing here, and we're going to go to the image there, and this is an oscilloscope, and what an oscilloscope does is an oscilloscope is actually a very simple thing. It's got a voltage generator that's got, remember those deflector plates in CRTs? This is a real CRT, yes? So one of them is a clock, and the clock simply takes the beam and sweeps it across the screen, and that rate is determined by this. So right now, it looks to me like it's stuck on 5 milliseconds per division. So it takes 5 milliseconds, 5 times 10 to the minus 3, or 0.005 seconds for it to sweep across one of those, okay? So that's our time scale this way, and I can change that time scale. So I can make it go faster, I can make it go slower, I can make it go incredibly slower. So it is 0.2, it's actually 0.2. Oh wait, what is it pointing at? I can't tell, it's 0.2. Now it's 0.5. I can make it go slower. I can make it go 0.2 seconds per division, 1001, 1002. It's going 5 of those, right? It's kind of chunking there. It's actually moving nice and evenly there. Okay, so as I speed it up, of course, this thing gets more and more spread out, right? So that's like a zoom on that axis, right? And then the vertical axis, what it does is it takes the signal that comes in, okay, and it just simply magnifies that signal to whatever it needs to do to deflect the beam up and down. So this, what it lets you do is graph, this is time this way, and up and down is a graph of voltage. So it's voltage versus time, right? And then there's a few other controls, but there is a scale control on that. And right now I've got it cranked up, it's 5 volts per division, and then my probe that I've got on there is dividing by 10. So it's really 50 volts per division is what it is, right? And so right now, coming out of the wall is, well, here's 0 here, so it's 1, 2, 3 times 50, plus a little more, maybe like 20 more, do you think? Right, it'd be my guess, right? So it's 50, 100, 150, 170 volts, right? Is that what we have here? Is that what, in North America, is that what we have? Is it 170 volts at our outlet? Because that's what I'm getting for the peak voltage. You thought it was 120, or sometimes you hear 110, right? Sometimes you'll see both of those, right? So what we're about here today is the notion that, I hate to erase your beautiful summary here, okay? But the notion that, to reconcile this whole thing, right, that we've got, if you look at this thing, we've got, what we're seeing here is that there's a peak voltage of about 170 volts, okay? Yet we have appliances that are rated at 120, right? So what it is, the 120 that you've heard is RMS, okay? So there's peak voltage, there's RMS voltage, and why it's RMS, I'll explain, right? But there's RMS voltage. RMS is like an average, and what it is it's a power average, okay? So if you use RMS voltages and plug them into the power equations, you get the right answer, as opposed to twice the right answer. And I'll show you why all this is, right? Okay, one last thing about the oscilloscope. Let me show you the scale here. I'm going to change the volts per division, and I'm increasing the sensitivity. Now it's going off the scale. I can't make it go smaller than that, right? I think I can turn a knob. There's like a knob that varies it continually, but it's uncalibrated, right? And then the other thing that's kind of fun is that it doesn't just trigger randomly. In other words, it doesn't sweep across in time. It sweeps across when a certain condition is met. And the condition is a certain voltage and a certain slope, right? So over here, if you look at the other side of this, there's other controls here. And one of these controls is the slope, the triggering here. So there's the level, and I can change where that thing triggers. So look at this. If I turn the knob, it starts sweeping across at a different voltage. And then if I go above the voltage that I have, it doesn't trigger, it just triggers randomly, right? So if you look at that, look at the left side there, right? Do you see how I'm changing where it triggers? And then I can also change the slope, I think. Let's see, pull. That's a negative slope, positive slope, negative slope, right? So anyway, that's kind of cool. How about a little applause for the oscilloscope? Okay, so one of the mini labs that we do in this unit is that I'll just set the oscilloscope out and I'll have you mess with it. Like try this, right? And it's just like a little station lab kind of a thing, like you did in 9th grade, only maybe you didn't. Okay, so, well, I don't know. I did that in physical science when I taught it, but you guys probably didn't take that. Okay, so let's go back to the alternating current. Let me unplug the extension cord of death here. There we go. All right, turn off our oscilloscope. By the way, nowadays, oscilloscopes are digital. They store images. They do fast Fourier transforms and stuff like that. They're just crazy. They're all computerized. This thing is just a classic, though. Okay, so let's hit the right arrow. And so it's not really important that you write down that it's 2 pi ft, but just the notion that it is sinusoidal, right? That our voltage at any given time is the peak voltage times the sine of 2 pi times the frequency times the time, right? Okay, and that just makes it like, you know, radians and stuff. And that the current is the peak current, whoops, right, times the sine of, it could be cosine too, right? That they are sinusoidal. And then the little knots like that, that means that that's the peak voltage. That means that that's the peak current. So we're talking about the very tips like that. And later on, we're going to talk about RMS. Does anybody know what RMS stands for? We do it a lot in science. We also do it when we talk about kinetic energies and stuff like that. It means root mean square. It's the root of the mean of the squares. Okay? So when I hit the right arrow here, you're going to see alternating current, yeah. Direct current, yeah. So direct current is like a battery. The voltage stays constant. Alternating current is this, what we're talking about today. Okay. Now, here's the deal, and I just want to explain this once, so pay attention. It's not all that important. What you really need to understand is don't use the peak. If you're trying to calculate the power, don't use peak voltage, don't use peak current, use RMS. RMS is an average. But here is why the formulas are the way they are, okay? Take a look at this guy right here. This is a graph of the current. The current goes positive and negative, and that's because it's a sine wave, right? It goes up and down, right? If you square the current, right, and where we're headed is, this is why Nathan taught power first, right, is that power is I squared R, right? So if we're heading toward power, if we square that current, notice that some of the time, the power is really, really high. And some of the time the power is 0, correct? So that's why we need to average, right? Why is it all positive? Why isn't the square of current go below 0? Is that because it's squared and negative numbers squared, right? So it looks sinusoidal, but I don't think it is. And notice that it's got like twice the frequency. That's because this peak squared is there, this peak squared is there, this peak squared is there, right? That's kind of crazy. Isn't that crazy? Now, if we were going to average that to get the power, do you see that if we cut these guys off and we sliced it there, couldn't these mountains fill in these valleys and that mountain fill in that valley, right? It's almost like West Virginia, isn't it?